Horizontal motion with constant acceleration. Prior to solving problems involving horizontal motion with constant acceleration, let us first review the concepts for accelerating motion and equation for non-accelerating motion. We say that an object is accelerating when the object speeds up, slows down, or that's decelerating, or changes direction. And we say the object is not accelerating when the object moves at constant speed or velocity along a straight path. For the equation for non-accelerating, we recall speed equals distance over time. Example 1.1. A car travels a distance d of 30 meters in a time interval t of 10 seconds. Find the car's speed. So we have here the given d equals 30 meters and time interval or t is 10 seconds. So speed equals distance over time. D, substitute 30 meters over 10 seconds. 30 divided by 10, execute using your calculator. You have 3 meters per second as the speed, constant speed. This is not accelerating. Equations for horizontal motion with constant acceleration. Equation 1.1, A times Tf minus T naught equals V final minus V initial. Equation 1.2, 2A times Xf minus X naught equals Vf squared minus Vo squared. And equation 1.3, Xf minus X naught equals Vo times Tf minus T naught plus 1/2 A times Tf minus To squared. A is also the instantaneous acceleration along X. A equals acceleration, elapsed time Tf minus To or T naught. V sub F is final velocity. V sub O is initial velocity at To equals 0. And XO is the initial position at TO equals 0. XF is final position. T naught is initial time, which is equal to 0 second. And T sub F is the final time. Our task now is to derive these three equations, 1.1, 1.2, and 1.3. But before we derive these equations, we first recall the derivation of our instantaneous velocity, because for equation 1.1, it is solved in a similar manner. So we recall the derivation of instantaneous velocity here. We have instantaneous velocity v equals xf minus xo over elapsed time. To do this, we start with the definition of instantaneous velocity v, which is v is equal to dx over dt. Transposing dt to the left, we have v dt equals dx. And so we apply integral to both sides of the equation. On the left, we have integral of v dt from t naught equals t to t final upper limit. And on the right, we have integral of dx lower limit x naught upper limit is x final. On the left side, we have v now is a constant because it's dt. So integral of dt is just t. So we have v t lower limit t o upper limit t final. On the right, we have integral of dx, and the answer to that is just x. Lower limit x naught, upper limit x final. So now we substitute the upper limit minus lower limit on the left side, and also on the right, upper limit minus lower limit v times upper limit t final minus lower limit t initial equals on the right side upper limit xf minus x naught. So we have arrived at our desired equation for our instantaneous velocity. Now we will derive the first equation for our horizontal motion with constant acceleration. We now derive equation 1.1, and this is derived in a similar manner as our previous derivation for instantaneous velocity. Here we have instantaneous acceleration A. We derive this by recalling the definition for instantaneous acceleration A, which is just dv over dt. And so we have dt here. We can transpose to the left. It becomes a dt equals dv. To simplify, we integrate. On the left, we have integral of a dt. So limits there t naught to t final. On the right, integral dv limits v naught to v final. On the left, a is just a constant because we have in dt, integral of dt is just t. So a t limits t naught upper t final. On the right, integral of dv is just v. So v naught upper v final. So again, we simply evaluate this by just substituting. Again, we simplify this by just substituting the upper limit and the lower limit. We have upper minus lower, the left side of the equation, and also on the right side, upper limit minus lower limit. So a times upper limit tf minus lower limit t naught equals, on the right side, upper limit v final, lower limit v initial. And so we have arrived at our desired equation 1.1. Horizontal motion with constant acceleration. We will use this equation. Next, we will derive equation 1.2. We now derive equation 1.2. 2a times xf minus x naught equals vf squared minus vo squared. To do this, we again recall our definition for instantaneous acceleration. A, it's just dv over dt, or first derivative of velocity with respect to time. But here, but here we'll use the chain rule. dv over dt can also be written as dv over dx times dx over dt. Here we can see that dx over dx is just 1, leaving dv over dt. So dv over dt is equivalent to dv over dx times dx over dt by chain rule. Notice here that dx over dt, this is just the velocity, instantaneous velocity, v. So the right side can be written as dv over dx, just copy the times v. Okay, so we now have a equals dv over dx times v. Multiplying the entire equation by dx. The left we have a dx is equal to dx dv over dx times v. So dx over dx is 1. We are now left with, on the left, we just copy a dx. On the right, it's just v dv. And now we simplify this by integrating the entire equation. So in the left, we have a dx, leaving a constant. So we just integrate integral of dx. But on the right, we have v dv. Okay, so on the left, we have a Integral of dx is just x, limits x naught to x final. On the right, integral of v dv, the answer to that is v squared over 2, v naught to v final as the limits. So just like before, we simplify this by substituting upper limit minus lower limit on both sides of the equation. So we have on the left side a times xf upper limit minus lower limit, substitute. On the right side, we have vf squared upper limit first over 2 minus lower limit, substitute v naught squared over 2. Now we can factor out the 1/2 on the left side of the equation. So 1/2 leaving vf squared minus vo squared. And on the left, we just copy, multiplying the entire equation by 2. So on the left, we now have 2a xf minus x naught. And on the right, we have 2 over 2 vf squared minus vo squared. So 2 divided by 2, that's 1. We now have our desired equation 2a xf minus x naught is equal to vf squared minus vo squared. This is our equation 1.2. We'll now derive the third equation, equation 1.3. xf minus xo is equal to v naught tf minus to plus 1/2 at squared. This equation can also be obtained using calculus, but here we will just use algebra. We recall the two equations 1.1, 1.2. We have for 1.1 a tf minus to equals vf minus vo. This is the 1.1. The second, we have 2a times xf minus xo equals vf squared minus v naught squared. Now what we'll do is we will get the vf of 1.1 and we are going to substitute that to equation 1.2. So transposing 1.1 to obtain vf. Obtaining vf using 1.1. I'll copy it first. A tf minus t naught is equal to vf minus v naught. We transfer v naught minus v naught to the left. That becomes plus v naught. Copy plus a tf minus t naught equals vf. And so we substitute this one in the equation 1.2. Let me call this one equation 1.1 point b. So basically what will happen here is this VF will be substituted to this, to the VF of 1.2. So I'll copy 1.2. What we say here, plugging 1.1 point B into 1.2. So I copy 1.2, 2A times XF minus X naught equals, the VF now becomes the 1.1 point B. We have V naught plus A, this is 1.1 point B, V naught plus A, TF minus T naught, then that should be a square. Copy the rest of 1.2 minus V naught square. So we just simplify. We'll now simplify this. On the right, we copy 2AXF minus X naught. On the left, we just copy. On the right, we simplify VO squared plus 2VO A TF minus T naught plus A squared TF minus T naught squared, and copy minus VO squared. So basically what we did here, this part, we recall a simple case of A plus B squared. When simplified, A squared plus 2AB plus B squared. All right, so we will now cancel or drop VO squared minus VO squared. All right, so we have now on the left side, just copy 2A times XF minus X naught. On the right side, you are left with 2VOA times TF minus T naught plus A squared times TF minus T naught squared. We divide the entire equation by 2A. Divide by 2A. Divide by 2A. All right, so left side 2 over 2, A over A, that's 1. And first term on the right side, 2 over 2, A over A. And here, second term on the right, A squared and A. So we now have our desired equation. Equation 1.3 on the left is XF minus X naught. On the right, we have VO, T final minus T initial. And then plus, I just express it as 1/2. That's 1 over 2. Then we have an A, and then TF minus T naught squared. This is our 1.3.